Hey, what's up, folks? So, I'm back. It's been a while. I moved continents. So I moved from America to Asia. I live in Thailand now. And I took some time off because I had to, get my affairs in order, get everything in order, sell my car, get rid of my apartment. To get back into the AI stuff, I left off where I built a vision transformer, right? So the goal is to build Stable Diffusion 3. And I'm going to start with Stable Diffusion XL. And then before that, working our way backwards, I'd like to build some of the the models that are foundational to Stable Diffusion, right? So there's a variational autoencoder, there are vision transformers, there's UNet, and then there's clip, right? So there are various technologies or techniques I should say that Stable Diffusion is comprised of, and I'm going to build these various components. Last, I built the vision transformer, and then I also decided to build ResNet because I might go down a few rabbit holes, right? I have time. So last we left off was a vision transformer, and then I decided to build ResNet, scale both of them up, and then train them on CFAR10 and compare how they perform. The theory being that ResNet 18 would converge to a better performance on the classification task more quickly. I tried to pick that back up. I just lacked the inspiration to do that. So instead of fighting against that, I decided to move forward with the foundational Stable Diffusion models, and I moved on to UNet. I'm moving on to UNet. So this video right here is going to be about UNet. So what is UNet? UNet it follows an encoder-decoder architecture. I would say the most important. So UNet was first introduced for segmentation of biomedical images. The segmentation task is it's a classification of each individual pixel in the image, right? So you're trying to identify where a certain object is in the image, and you output, if you have n classes, you output, for each pixel, there's a softmax distribution over n classes, as opposed to, right, one classification for the entire image. So UNet was introduced for segmentation of biomedical images, and it's the backbone of Stable Diffusion. I'd say the most important component of the UNet architecture is the skip connections from the encoder to the decoder. So if I had to talk about UNet on a high level, what it is basically it learns to perform image segmentation by learning the what and the where. So the encoder learns the what, which are these abstract feature maps in this latent space, right? So you essentially have these convolutional layer, these convolutions that you have these convolutional layers that downsample your image and increase the feature maps until it learns this abstract representation in the latent space. And it has 4 layers, and then the decoder has 4 layers where it upsamples your image using a convolution transpose operation. It upsamples, and then at each layer there's a skip connection from the mirrored layer in the encoder to the decoder. So it concatenates it takes the what from the encoder, and it takes the what that it's learned, which are the feature maps, and it concatenates it with the where information from the encoder, right? So it learns the what, and then the encoder passes the exact spatial location of the objects in the image. So it learns the what and the where, and through that process, that's how it learns to segment an image, right? It needs to intelligently learn what the makeup of an image is, and it does that by learning the what and the where, which are the skip connections. So the skip connections are the most powerful part of UNet. And yeah, so we are going to build UNet from scratch. There's going to be a lot of repeated code in a lot of my videos, right? Repeated PyTorch code. So as I accumulate more videos, I'm not going to repeat, you know, some of the the matplotlib code and maybe some of the training code like after I do it a certain number of times, right? So probably after I do it once in each video, like each new thing I add, the next video, if I reuse that thing, I'm just going to, right, in the next video, if I revisit that, I'm just going to reuse the code and then I'll point folks to the code in the previous video. In this, code, I'm using weights and biases, which is an extremely useful tool for machine learning training and inference. I am using config files now, right? So for a server configuration and a local configuration so that I don't have to do any of this manual, I don't know, separate code files or manual coding on the server. I just have a config file. I have whatever command I'm going to use to run the code. I'm going to pass in a config file to switch it between server and local depending on which environment I'm in. Yeah, that's all I can think of right now. So I think, yeah, let's get started. Oh, right. I also know how to use my iPad with this software now. So I'm going to be explaining a lot of the math. There isn't too much math in UNet, but I am going to be drawing the model architecture because it's easier to explain. And I'm also going to explain the convolution transpose operation using some pictures because it's much easier to understand that way. I also tried to build the convolution transpose operator from the ground up, but it got really hairy in PyTorch. And so I time boxed it, and because I couldn't figure it out in that time, I just was like, this is kind of going outside of the scope of what we're trying to do here. So perhaps in the future, I'll take another stab at it and we'll see if we can use PyTorch's fold or unfold to, build this convolution transpose that sort of upsamples your image and decreases the channels. But for now, just going to use PyTorch's convolution transpose function. So yeah, that's it. Let's get started. This is what UNet looks like. Looking at UNet, I highly suggest you read the paper. So I highly suggest you read the paper. But for now, let's just take a look at the general architecture. So it has these double convolutions. These are two convolution operators where it basically learns feature maps, and then there's a ReLU operation. So it basically goes from convolution to ReLU and then to convolution to ReLU, right? So that's how it learns the interactions between the features. And I'll explain a bit more about why stacked convolution operators are powerful. So each layer, and then this is a max pool operation here. So we go from convolutions to max pool that shrinks the dimensions, right? And so here are the dimensions. So we have a 3-channel image on the input in 3 channels, RGB, right? And then it immediately expands to 64, 64. And then the max pool operation shrinks the size of the image. So we go from 572 by 572 to 248. In my network, we're going to start with 128, and then we're going to shrink to 64, and then from 64 to 32. So the only thing you need to know is that for the input layer, the double convolutions learn feature maps more efficiently than if you were to have like a very large kernel. And then the max pool operation shrinks sort of downsamples the image so that the convolution, the convolutions can learn higher order features, right? So, and that's basically the general architecture of the encoder. You go from convolution to downsample, convolution, downsample, convolutions, downsample, convolution, downsample, until you have this image representation in the center, which you can call sort of a latent space. You can call latent features that describe your image. And then on the other side, you have an up convolution, right? This green arrow, which is a convolution transpose operation, which I'll explain. So this basically upsamples your image, and it so you upsample your image, you concatenate it right here with the image from the encoder. So you upsample your image, and you decrease the number of channels at the same time. So this goes from 1024 to 512, and then you concatenate it with the 512 channel image from the encoder, right? So now you have 1024 again, which represents your, which basically is the exact position of everything in the image, and it's like the exact details of the image from the encoder with the sort of abstract general representation of the image at this point that the decoder is learning, right? And then you concatenate those together and you send it through a double convolutional layer so it sort of refines the image. So this is upsampling, this is fusing, and then this is refining. So you upsample, fuse, refine, upsample, fuse, refine, and then you do that until you get your reconstructed image on this side. So I redrew the network exactly in the way that I'm going to build it. So it's not the exact UNet, but it's very, very close to it. And all of the important things from UNet I'm implementing. So I color coded things, right? So any of the pink, salmon, I guess you would call this, any of the salmon color represents a double convolution. So just know that it's going through two convolutions here, and two ReLU activations. Insert the original image in here. So, okay, so here we have the original. So I think there's some padding going on here, such that the size of the image is shrinking slightly. I'm keeping the size of the image the same throughout the double convolution operation. So just because I don't know, I just think it's easier to track this way. So we can see here that we start with the input of 3 channels. And then we immediately, the first convolution operation, we expand to 64 channels, and then we keep 64 again. So 64 channels, we send it through ReLU activation, and then we learn some additional interactions by sending it through another convolution. Now, why double convolutions? You'll see this commonly in computer vision. One is the increased receptive field. So the kernel that I'm using, that we're going to be using here, is a 3x3 kernel. Um, so So you can increase the receptive field by stacking convolutional layers without increasing the parameter size. What that means is if you want to calculate the receptive field for two stacked convolutions, it's the previous receptive field plus k minus one of the new receptive field. So say you have 3 by 3 going to another 3 by 3. That's 3 minus 1, 2 plus 3, right? So then 5. The new receptive field is going to be 5. It's going to be 5 by 5, right? So, and that's 5 by 5 is, so the total number of parameters is going to be 3 times 3 plus 3 times 3, which equals 18, as opposed to if you had, right? And remember, the receptive field is 5, right? But if you had a 5 by 5 kernel, it would be 25 parameters. So that's 18 parameters that, you know, not only have a higher receptive field, so that's the first, but also they learn more nonlinearity. So you get like, it's like a double whammy, right? You not only increase the receptive field, but you also learn more nonlinearity, right? Because you're going, you know, 3 by 3 kernel with ReLU, and then you're, right, so that's your nonlinearity, and then you're sending it to another 3 by 3 kernel in ReLU. So you're learning more complex interactions. So double convolutions are more powerful than just using, you know, a larger kernel. Yeah, I think that's the most important thing of why double convolutions. I'll also add these notes to the repository, the PDF to the repository, so you can check it out. Back to the architecture, max pool is going to be in blue, right? So you have double convolution, max pool, double convolution, max pool, like I explained before. You can see the dimensions of your image. I outlined it clearly, so you can see exactly what's happening, and it mirrors the code as well. And then the orange is a and then the orange is the skip connection. So you get to this middle layer here that has 1024 features, and it's 8 by 8. And then again, you upsample with the transpose convolution operation, which I'll go over. You and then you combine that, you fuse that with, so you upsample and you shrink the features at the same time, and then you concatenate that with the exact feature map from the encoder, and then you refine with the double convolution operation here. So this, actually I should make that refine to be the same color as the double convolution operation. So color, I believe it's, yeah. Okay, and then you refine with double convolutions. And then you output 3 channels that represent your logits for the prediction classes, right? So the segmentation task is you're going to have you know, a class for each, you're going to have you know, n classes for each pixel, right? So each pixel is going to be, you know, either background. So in the case of the data that we're going to be using, which is the Oxford 3 pet data, the 3 classes are the 3 classes that each pixel could be is either a pet, a background, or part of the boundary, which the boundary is neither pet nor background. It's sort of like a gray area that's like that you define for your ground truth data such that you're sort of giving your model a bit of grace. So it's like, oh, we don't know whether the class, it's like right on the edge. It could be either pet or background, right? So those are the three classes. And then you're going to take a softmax to determine which of the logits is the highest. And that's going to be the predicted probability of which class the pixel is going to be. So I realized I didn't have the objective function in my notes. So I wanted to just write that down really quickly and just go over that so right? So this might change. Yeah, I might change this depending on how the model performs. Well, right now I've already obviously coded it and run it. So right now there's a certain score we're going to use called the dice score. Which actually I'll explain next. But that is around, well, I've gotten it to around 0.75, and which I would like to get a little higher. So it's possible that I'll add the dice score to the loss function, or I'll use the dice score as the loss function. But right now, I'm just going to do cross entropy loss of the pixel classification for whether it's the cross entropy loss for the correct pixel classification. So what that looks like is we have C classes. In our case, that'll be the classes will be pet, background, boundary. So our classes are pet, background, and boundary. And so our network is going to output logits, right? So the logit dimension is going to be these three right here. And it's going to be for each pixel. And then we have a ground truth label at each pixel represented by L of X. So our logits are A of X and our ground truth pixel is L of X. And then we're going to calculate the cross entropy loss, right? Which is essentially, so if we take a softmax across the channel dimension, right? If we take a softmax across the channel dimension for the logits, right? So we're going to normalize the channel dimension across the logits, right? And the cross entropy loss is going to be the prediction for the ground truth label pixel. Like what is the probability of the ground truth label pixel? And then we do the negative summation of across all pixels in that image, and that gives us our cross entropy loss, which we're trying to minimize. So it's a standard, it's the same thing as doing classification of an image, but we're just doing classification of a pixel. So for a single image, we'll do the summation of the prediction of the ground truth label across all pixels. And the dice score that we're going to calculate, which gives us a notion of how well our model is performing. So the reason why we're not going to do accuracy on a pixel level is because for many segmentation tasks, including this one, the majority of your the majority of your pixels are going to be of the background, right? So you have a class imbalance, and that's going to, therefore accuracy is a sort of, it's a biased, I guess, it's a biased or distorted, it's a biased or distorted score. So, and the reason is because, accuracy is, the number of correctly predicted pixels out of all pixels. And if the majority of your pixels are of the background, the majority of the denominator is going to be of the background. And so, if your model learns to predict a bunch of your model can just learn to predict background pixels, to predict the majority of your pixels to be of the background, and it's gonna give you it's gonna give you a signal that it's performing well, but it just learned to cheat, right? So we want to use the dice score, which is so the dice score is actually the harmonic ratio between precision and recall. So let me make this a bit more clear. So maybe I'll so the dice score is 2 times precision recall divided by precision plus recall. So it's the harmonic ratio. So it's just the average between precision and recall. And that ends up being this right here. And so I want to talk about intersection over union and dice at the same time because they're very closely related. Okay, so intersection over union, which is the same thing as Jacquard similarity. So you'll hear it referred to as Jacquard similarity. So for intersection over union and dice, so let's look at intersection over union first. So A is predicted pixels of it's the predicted pixels of one class. So remember, we have 3 classes. We have pet, background, boundary. We're not gonna look at boundary for now, and I'll explain why later, but let's pick one class. Predicted pixels in class, and B is ground truth pixels in pet class. Right, so the intersection of over union is, sorry, IOU is the number of pixels that are in the intersection of A and B. So it's the number of pixels that are, it's the true positives. It's the pixels that are correctly predicted to be in the pet class, and the pixels that are actually in the pet class, right? And then the denominator is it's the union. So it's the pixels that are in the predicted pet class or the ground truth pet class. I think a better way to think about it, it's kind of confusing to think about it logically, so it's easier to think about it with an image, which is what I drew here, right? So if the circle on the left are the predicted pixels in the pet class, the circle on the right are the actual pixels in the pet class. The intersection is where they overlap, right? And then the union is the combination. It's the pixels that are in both, also including the intersection, right? And what we want, right? So the intersection over the IOU score, the IOU score is between it's between 0 and 1. It can be 0 all the way through 1. And what happens is, as the IOU score moves from 0 to 1, right? That means the sets are more overlapping, right? So that means your predicted segmentation mask for pet. So this is your predicted segmentation mask for pet. This is your predicted segmentation mask, your actual ground truth mask. As the score moves closer to 1, the more your masks overlap. So as your score moves closer to 1, the more your masks overlap. I honestly think that's the best representation that you're going to get of what this score means. And then dice is basically 2 times. It's the same. So intersection over union reduces to, so and dice is, so your intersection over union reduces to this if you're going to write it in terms of true positives, false positives, and the dice score is just 2 times the false positives, right? So it's this equation just with 2 multiplied by the true positives. And basically what that means is one way to look at it is it's more, it gives a higher weight to overlapping masks. Another way of looking at it is intersection over union is less forgiving when the intersection over union score is less forgiving when the masks don't overlap. That's another way of looking at it. Dice is like, it weights more heavily overlapping masks. And another way to look at dice is the harmonic ratio between the precision and recall, where precision is, right, remember, precision is the probability that it's the probability that your prediction is 1 given that the ground truth is 1. And that is your true positives. I've always found this the easiest way. I remember precision and recall was so hard for me to understand at first. Like, I don't know why it was so hard for me to understand. They're like, oh, true positives, false positives. It's like, oh, what the fuck? You know what I mean? It was like, but then I saw this as a definition for it, and it just made so much more sense, like conditional probabilities. And then you can derive true positives and false positives from the conditional probabilities. So precision is out of all the things that you've predicted to be one, how many things are actually one? Right? So all the things that you predicted to be one are your true positives and your false positives. So all the things that are the universe of things that that are predicted to be one are true positives and false positives. And then how many of those are actually one? Those are your true positives. Looking at recall is out of all the things that are actually one, which are your true positives and your false negatives, how many did you correctly predict to be one, which are your true positives? Going back to the dice score, dice is a harmonic ratio between precision and recall. So if you substitute this in for precision and this in for recall into this equation and you simplify, you'll get this. So first, we're going to use cross entropy loss to we're going to use cross entropy as our loss function. We're going to track dice score as per epoch to see, along with the loss, to see how the model is performing. And then that's kind of where I stopped personally. And then I'm gonna try to push I'm gonna try to get better performance out of the model. So I might need to add dice loss to, I might either need to use dice as the loss or add it to the cross entropy loss for stability to better improve performance of the model, but we'll see. So just a quick review. UNet, we start with our image, 3 channels, 128. We send it through double convolution to learn feature interactions, and then we downsample the image so that the double convolutions can learn higher and higher order features. And then we send it all the way to a latent space that is of 1024 features, and then we upsample so we upsample the image and we decrease the features at the same time, and then we concatenate that to the mirrored encoder representation so that UNet knows exactly how to reconstruct, so that the decoder knows exactly how to reconstruct the image. So it has a general representation of an image here, and then it has exactly where everything goes here. So that way it learns both at the same time. Then you send it through a double convolutional layer to further refine the image. And then you basically do that for each layer until you get to an output which has the logits, which is a prediction of which class that pixel is going to be in. You take a softmax over the channel dimension for all pixels, and then you compute the cross entropy loss. Which basically is a summation over all pixels of the probability of the ground truth label. So it penalizes low probabilities for the ground truth label, right? So you're trying to minimize this loss, which is going to ensure that the probability for the ground truth label is going to be as high as possible. And then we're going to track the loss per epoch, but we're also going to track, so we're going to compute our epochs in terms of mini batches, right? And then we're going to get the loss on a mini batch level, and we're also going to take the dice score on a mini batch level, which is the harmonic ratio between the precision and the recall of your predicted pixel for a pet class and your ground truth pixel for a pet class. And we're going to do that for each class. Actually, we're going to take the average of the two important classes, which are the pet class and the background class. I'm actually going to code a little bit more to separate these two losses so we can actually track the dice score individually for the pet and the background instead of averaging them together. And then some other important things to know is the dice score is the same as the intersection over. I think the best way to understand the dice score is to understand, or the easiest way to understand the dice score is to understand the intersection over union or Jacquard similarity. The easiest way to understand that is to look at this right here and to see that as the score goes from 0 to 1, the more your predicted mask and your ground truth mask overlap. And then once you understand intersection over union, dice score immediately follows because it's just 2 times the false positive. It's 2 times the false positives in the numerator and denominator, which basically means that it weights overlapping masks more heavily. Another way to look at that is that intersection over union is less forgiving in terms of masks. In terms of it penalizes non-overlapping masks more heavily. And then just as a quick review, this is a nice way to derive precision and recall is in terms of conditional probabilities. And if you want to get the dice score, you plug these equations into the harmonic ratio of precision and recall, and you'll end up with the dice score. So, okay. I hope that was a decent, I need to do the transpose convolution operator. Okay, so I'm going to explain transpose convolution really quickly. So the way the operation works is it takes, okay, so let's say you have, your input image is 4x4 and it has 6 channels going in, and then we want the output dimension to have 3 channels, and then the width and the height is going to be determined by this equation. So we plug in for height, we plug in 4, then -1, that's 3. Stride is going to be 1 in this case. In UNet, we're going to use a stride of 2, but in this case, we're using a stride of 1. No padding, and then output padding, which simply just appends a pixels around your output image. That's going to be 0. The kernel is going to be of size 2. So this gives us an output image of size 5 pixels. And the way the operation works is whatever the pixel value is here, so we're just going to make it simple and put 1 here. Then we can put 2 here, I guess, just to show a different example. So you're going to multiply 1 by each of these and then copy the value here. So this is how it expands the image, right? We're going from 1 pixel and then to a kernel that upscales that pixel to a 4x4 dimensions. We're going to do the same thing for the 2. So basically the 2 is going to project into the kernel is going to project this 2 onto this space right here, and then the values that are overlapping are going to be summed here. So it's going to be 2 times 1 and 2 times 1. So this is going to end up being, 2 and 2 is, so 2 and 2 is 4, 3 and 2 is 6. So we're going to have 4 and 6. And then this is going to be 2 plus 2 and 3 plus 2. This is going to be 4 and 3 plus 2, 5. So 2 times 1 plus 2 that was there, and then 2 times 1 plus the 3 that was there. I hope I'm doing this math right. But you get the idea. And then this cell right here, whatever value is inside here, is going to be projected by this kernel right here onto this space, and any overlapping values will be summed. And then, you know, for this, it's going to be projected here. All the overlapping values will be summed. And that's how your image is upscaled. Now, the thing that it's kind of hard to find online, but that I think is crucial to understanding this is how multiple channels works. So for each input channel, you're going to have C out number of kernels. So for this input channel, this green kernel is going to work exactly how I described it. So this kernel is going to, for each of these pixels, slide across this entire image, and then you'll have one of these kernels for each channel, and then, you know, for this channel, it's going to project across the whole image, right? For this channel, it's going to, and every time it does that, it's going to sum. Every time, so let's say this value here is going inside here and being projected to this space, it's going to sum on top of whatever values are there right now. And that's how we get one channel. And then this is the second kernel for the first channel. It's going to do the exact same thing, but for this channel. And then you'll have an orange kernel for each of these channels that projects and sums onto this. An orange kernel here that projects and sums onto this. An orange kernel for actually, so here's the orange kernel for this one, projects and sums onto this. And then you'll have a blue kernel for this one, projects onto this, a blue kernel for this one, projects onto this, a blue kernel for this one, blue kernel for this one, boom. I mean, that's how it works. It's not clear at first, but that's exactly how it works. The way you can think of it is these are all different types of paintbrushes, and then a kernel defines exactly the style and stroke intensity and thickness that the paintbrush will actually brush in. And then this will be a canvas. These will be canvases. So basically, all 6 of your brushes will paint will be mapped to a different unique style, which is a kernel. And the first one will paint across this, and then the second one will come over and paint across it, and then the third one will add. They'll each keep adding their own unique styles and flavors to this canvas. And in the end, you'll be left with 3 canvases that each 6 paintbrushes will paint across, but in different styles, which are the kernels. So am I missing anything? Right, so you have your input, which is 4 by 4. So 4 goes here. So if we're determining, let's say, height, 4 goes here. And then kernel size, stride is 1. Stride goes here. Kernel size goes here. And then there's 0 padding. This is 5. Gives us our output. So that's it. That's the transpose convolution operation.